How's it going, everybody? All right, so what we're going to do for the second half is we're going to start digging into what makes elements act like the way they are, right? So we're going to look at where they are on the periodic table, and we're going to try to be able to predict some of their chemical and physical properties based on where they are. Because if you remember, based on the law of periodicity, we had to hit return every time they started like kind of repeating themselves, and we got rows and we got columns, right? Those are the two main characteristics of the periodic table: rows and columns. And so we're going to look at what's happening inside of a row, right? So we can predict what things are going to be like on this end versus this end, sort of like compared to one another, like relative to one another. And same thing with the columns, right? We're going to see what's going on inside a column, the one that makes them so similar, and two, what makes them a little bit different. So what I want to do is, bam, start right here with this stuff. And then what I want to start with is this thing called atomic radius. Now, atomic radius basically just tells us how big the atom is, okay? And so much depends on like the size of an atom. It's not even funny because for an atom, ooh, coffee burp, excuse me. So like the nucleus is like right here. You guys get what I'm saying? Like right there's the nucleus, and out here is where we have the electrons, right? And there's an attractive force that's holding them together so the atom doesn't just like totally fall apart. Now, this attractive force between the positive and negative works exactly like a kitchen magnet, right? If it's very, very close, it's very strong. It works like there's a lot of force. But as soon as you start breaking away and getting further apart, that attractive force drops off. I mean, does that make sense? We all know how kitchen magnets work. So if an atom is very big, it can, like, that attractive force is incredibly weak. There's almost no pull on those outer electrons, whereas exactly opposite, but the same thing. If the atom is very small, right? If the radius is itty bitty teeny, that means that those electrons and the protons are very, very close to one another. So there's quite a big like pull or attractive force between one another. Okay. So the atomic radius is actually half the distance between two adjacent atoms. And what we do is we actually measure the distance between the nuclei, and then we like cut it in half, right? Because nuclei are where all the mass is. Remember, electrons are like a cloud, and you can kind of see with this, it's like the edge of the cloud is really fuzzy. Like you can't tell when fog begins or ends. Same thing with this. You can't tell where the electron cloud begins and stops because cloud. So we just use X-ray refraction, which is a fancy way of looking at shadows through an X-ray, and we can actually measure the distance between two separate nuclei. Amazing stuff if you know your trigonometry really well. So this thing, this radius, what gives atoms their radius? Well, there are three things that influence it, and the first is the number of energy. Let's put this here, the number of energy levels. More is bigger, obviously, right? So there, man, stakes a lot. I'm telling you what, the jumpies here. Give me a second. Boop. So, I was saying, here's the nucleus, right? Now, if you have two energy levels, it'll be 1, 2. It'll be about that big, right? Now, if you had 4 energy levels, there's your nucleus. You'll have 1, 2. It's about the same. 3, 4. You guys get what you guys can pick it up what I'm putting down here. I certainly hope so. It's not super duper rocket science. The more layers, like the bigger it is, okay? The next one is the number of protons. Now this one only works inside the same period, right? And what's happening there is the more protons you have in the nucleus, the greater the proton pull there is. Does that make sense? So if you only have 3 shells, and over here you have like, I don't know, 5 protons, but every time you take a step to the right on the periodic table in a row or a period, you're adding 1 more proton. So that's adding just a little bit more proton pull. Then you add another proton and add a little bit more proton pull and add another one and add a little more proton pull. So as you move from left to right on the periodic table, what actually ends up happening is you're increasing the amount of proton pull in the nucleus. So it kind of shrinks it down a little bit. The third, shielding effect. This third one is shielding. Shielding effect works a lot like papers on your kitchen magnet. Remember when you're a little kid and you do like something really awesome in school and you brought it home, you're like, hey, mommy, daddy, look what I did. And they took it and they put it up on the kitchen refrigerator, right, with a magnet. And the next day you came in with something new. You didn't want the old one taken down, so you have to put up the new thing. Great. Now you do this 3 or 4 times in a row. You've got like 3 or 4 pieces of paper there. Eventually that magnet stops working, right? Because there's something physically blocking it from like getting to the refrigerator. There's something blocking the magnet from the refrigerator. That's a lot like what shielding is. But in this case, instead of like magnets in the refrigerator, it's electrons and protons, right? So basically what it means is when the electrons are way out here and it has to like go through, it has to literally be able to see through several layers of other electrons, right? More energy levels, more clouds. It's really hard to see in there. You can almost think of it as a light, like if protons were a light and this electron needed to see that light, it's really hard to see the light through 3 layers of clouds. It just gets dimmed, right? The clouds get, like the light gets dimmed, just like that proton pole is getting dimmed because it has to sort of break through those 3 layers of negatively charged electrons, right? So shielding, the definition, is the blocking of proton pull by the inner shell of electrons. And so these would be the inner shell. You've got 1, 2, 3 inner shell layers, right? So that's what I mean by inner shell layers. And what happens is that this guy, the outermost electron, has to look through, right? It's got to get through all 3 of these before it can sort of like see the proton to get that proton pull. You guys understand what I'm saying? I hope so. It's almost like going to a football game and there's like 5 rows of people in front of you and they're like in between you in the game, so you can't see the game. Why? Because they're physically blocking you. That's a lot like what shielding is. So what happens in a group? Well, here are the group trends. Now remember, group, this here, right? That is our vocab word, our group or our family. That's our up and down. So as we increase the atomic number, right? Now this is the thing, is the way that we're going to determine whether we're going up, down, left, right is almost always going to be based on atomic number, because that's how we identify the elements, right? So as we increase the atomic number, in other words, we're heading from top to bottom, each atom has another energy level. So the atoms get bigger, right? So here is hydrogen. It has 1 little energy level. And lithium, it's got 1, 2 energy levels. Sodium has 1, 2, 3 energy levels, and 4 and 5, and so on and so on. So this is the trend inside a group or a family. I call this, the way that I remember this is with a, oh wait, not with that. The way that I remember this is that your group or your family makes a chemistry. Get it? A chemistry. It's a chemistry. Chemistry. Because, you know, are you guys not with me on this one? A chemistry? No? Am I the only, get it? A chemistry? Get it? Chemistry? Right? Because it's like skinny on the top, like that, and it's all fat and wide at the bottom. Am I the only one who thinks that chemistry is pretty awesome? Be quiet. Chemistries are awesome, man. You got to know the trend. You got to know this trend, okay? So what that means to us as chemists, if you look at hydrogen way up here, those electrons are really close to the nucleus, so it's going to be held on a lot tighter than... Look at rubidium. Look at that thing. Those electrons are so far away. Rubidium, man, dude, rubidium is reactive. It cannot hold on to its electrons. They are so far away. There's so much shielding that those electrons, I mean, you just like brushy, dude. Rubidium, it just loses its electrons. It literally can't hold on to its electrons. It's just too far away. So that's the deal. In the family, it makes a chemistry in the family. All right, moving on. Because the other thing that we need to look at is the periods, right? Because the groups go up and down, the periods go left and right. So going from left to right across the period, the size gets smaller. So as you move from left to right, it's going to get smaller and smaller because the electrons are in the same energy level, right? Like there's no like, wait, Na, sodium, 2 I think? No, 3, all right? So there are 3 energy levels in here, right? But every time we come over 1, we're we're adding +1 more, right? Plus one more, plus one more, plus one more. We're adding one more proton into that nucleus every time we take a step to the right. Does that make sense to you guys? And so every time we're adding one more proton, we're adding one more bit of proton pull, and that pulls those electrons in closer and tighter. And so as we go this way from left to right, if you notice it gets smaller and smaller, man, these guys hold on to their electrons like crazy. They do not let go of electrons because look how close they are compared to something like sodium. Man, sodium, dude, look how far out those electrons are compared to something like chlorine. That's like, dude, that's like night and day there. You know what I'm saying? Great. I'm glad you know what I'm talking about. So this is all about atomic radius, right? It's like the radius of an atom. So guess what ionic radius is? Yes, it's the radius of an ion. So ionic radius is basically the size of an ion, right? I mean, that's really what it is. It's the difference from the nucleus to the outer shell of an ion. It tells us how big an ion is. Now, here's the deal. We have two kinds. We have cations and we have anions. Now, remember, cations, you have this T to say that it's a positively charged ions, right? Now, if it's going to be positive, it has to lose electrons, right? Now, when atoms lose electrons, they lose an entire energy level, right? And that is why they are smaller. That's why they're smaller. So cations are small because they lose the entire outer shell. And they do that because the shell underneath has their magic 8 valence electrons that makes them super duper crazy stable. You guys understand what I'm saying? So cations, or positively charged ions, lose electrons, but they lose the entire outer shell. Whole thing gone. Boop. So they shrink down a little bit. Now, same thing, only completely different are these guys over here, the anions. Let's try this one. So remember, N is for negative, so the anion, right? Anion. This forms by gaining electrons, right? Because that's a negatively charged ion. Now, this works just like putting air in a balloon, right? If you have a cloud and you shove more electrons in there, they kind of blow up a little bit, especially because if you add electrons, it has to go into the same energy level. And they're all negatively charged, so they don't want to be near each other. So they kind of have this like negative repulsion thing that kind of blows them up a little bit. Right? Does that make sense? So they have the same outer energy level, and all the electrons are being shoved into it, and that makes a negative ion bigger than the atom that they came from. And I hope that makes sense because, I mean, you're just adding stuff to it. Now, the thing is that atoms gain and lose electrons to get the electron. This is a clutch thing to get inside your head. They are doing it to get the electron configuration of noble gases. So if you look up here, like chlorine is really close to argon. It's probably going to do everything it can to look just like argon. Same with sulfur, same with phosphorus. They try to make themselves look like the noble gases because the configuration of noble gases is unbelievably stable. There is no more atomic stability than to look like a noble gas. Apparently 8 is like atomic bling. I don't know. I am not an atom. I can't really tell you. Whoa, that's it. Oh my gosh, dude, 13 minutes. I'm looking at the clock here. You guys are getting all scot-free on this one. We'll tell you what, some easy stuff. Yeah, except for all the element ID stuff and everything. But anyway, here's what we're going to work on next are what are the trends in the periodic table, because that's what this whole like half of the chapter is about, the trends. Trends meaning like atomic radius versus top to the bottom, like atomic radius like left versus right, all that kind of stuff. And then the atomic radius is going to lead into some other chemical and physical properties. So if we have atomic radius locked in our brain and we own that, everything else comes from the atomic radius. So this is like the groundwork for what we're going to be doing for the second half of the chapter. Thank you for tuning in. Man, I hope you guys have a wonderful day, and I will see you on the flip side. Deuces.